Thank you everyone for attending. I'm Miquèl. I work for Bootlin, and a few years back I kind of fell in love with NAND chips. As part of my daily job, I was involved in the development of the NAND subsystem, which I now maintain and help maintain the MTD subsystem as well. So this presentation is going to be mostly focused on flashes. People might no longer be used to them, even though they were quite familiar in embedded systems a few years back. They might have been replaced by eMMCs in some designs, but there are still designs where they are relevant to use, especially for their price. The cost might be important. So, well, disclaimer, I like NANDs more than everything else, so I might be a little bit NAND-focused overall, but I will also talk about NORs. EPROMs have been progressively replaced by parallel NORs in the first place, so they were way cheaper overall. Then another technology arrived, which was the NAND technology. Initially, it was wired with a parallel bus. So overall, the density was way higher, and maybe the speed was better as well. But it comes at a cost, the cost of the stability. So it requires a little bit more handling. We have a real subsystem for that, the MTD NAND row. That's where the core is, to handle in a generic way all the specificities of the row NAND chip. The row folder was created quite recently. I mean, Linux has been there for 30 years, and this subsystem for a few years. On the north side, they've been replaced by SPI NORs mostly. Today, we only see SPI NORs. So they are using a common bus, the SPI bus, with existing controllers. So it was quite easy to transition. SPI NORs are supported under drivers MTD SPI NOR. And nowadays, we see more and more the use of SPI NANDs, which might also replace parallel NANDs. So they are supported, and there is a subsystem under drivers MTD NAND SPI. Both SPI NOR and SPI NAND use the same layer called SPI MEM, which was actually introduced for SPI NAND in the first place, to make those drivers that were SPI NOR controllers less SPI NOR oriented, because it doesn't really make sense to have a SPI NOR controller. Nowadays we talk about SPI memory controllers. All right, so I'm going to focus on the improvements in this area, and this presentation will be split into two parts. A small part about the storage, of course, it's important, and a bigger part on the performances. So first one might be, to mention, might be the OTP support. OTP stands for one-time programmable, and many flashes have one. There are two types, factory and user OTPs. The factory OTP typically contains a unique factory identifier, whatever, something you do not master. It's only readable, whereas the user OTP is writable. Not only a single time, despite the name, which is a bit misleading. There is usually a locking feature, so you can still erase and rewrite the OTP several times if you need, especially for development purposes. So MTD supports that. There are those hooks, get info, erase, write, read, lock, and then the subsystems implement them as well. SPI NOR since 5.13 and SPI NAND since 6.15, so that's pretty recent. On the storage side, an important factor, of course, is the density. So you're probably aware there have been SLC NANDs, which have been there forever, so single-level cell where you store a single bit in a NAND cell. That's the safest approach. And then vendors have started stuffing more bits in the same cells. So that makes the overall storage way more dense, but also way less stable. So we support SLCs in Linux. TLC, QLC, no way. MLCs, it's kind of a mixed situation. There are issues in supporting MLCs. There has been a talk about that already, but rapidly, the 2 bits that you might find in an NAND cell, they do not belong to the same page, which kind of doesn't simplify the support. You have to know the pairing scheme, and you have to make sure you program the first page before the second page. Plus, it is, well, MLCs in general are more likely to be disturbed by, well, almost anything. So it's an order of magnitude less stable than SLCs. In order to support those MLCs anyway, it's been decided that a pseudo SLC mode will be used. So we cut in half the capacity of the chip. So we have, well, less density overall, like an SLC, but at least we can use them with Linux. So that's something that has been out of 3 for many months, even years, and has been merged in 5.8. The fact that the density has become higher in NANDs led to more retention issues on MLCs, of course, but not only, also on SLCs. And the problem is that when the more thresholds you have in your NAND cell, so in your internal circuitry, when you try to guess what is the actual level and derive bit values, you might be too close to a threshold and get a bit flip. So the NAND read-retry mechanism was introduced by vendors, which allows, if a read is unsuccessful, to try again with a lower threshold. So that can be repeated with several thresholds until you get the actual data. So even though you might think the data is gone, there are still interesting levels to sense, and you may recover your data with this kind of feature. Now about the speed. So I've split this into 3 parts. But before I explain those different areas of improvements, let's just make sure we talk the same language. So I've been using this tool, Flash Speed, for making my benchmarks. So I will give you numbers, because people like numbers, and they have been captured with this tool. The tool is really dumb. It looks at the clock of the system, does some operation, looks at the clock again. So it's very sensible to system load, and in order to get meaningful results which are repeatable, which is the most important part for me when I do those tests, you have to keep the system idle, use a higher priority, and somehow disable CPU management, because it really interferes with the measurements. Of course, CPU management, CPU power management is important. It matters, but for this kind of measure, it's a problem. The two perf figures that you have here, so on the left, it's without a feature. On the right, it's with a feature supposed to increase the bandwidth. The result was showing the opposite, and perf helped me understand what was going on. And that's what led to those spikes here. So they are expected because there are more control commands on this version than the former one. But the thickness of those peaks indicates that we were spending way too much time doing CPU idle entries and getting out of it. So it was on a downstream platform. I haven't investigated too much, but that was clearly having a strong impact on the benchmark. So here is a flash chip connected to a host. On the host, you'll have a flash controller, whatever that is. It can be a parallel controller, it can be a SPI controller. On the flash, you would have a memory controller that processes the commands, some kind of cache, a volatile memory where you would write the data that gets out of the flash array, which is the third square. So of course, the third square stores the data in a non-volatile manner. A read from a flash, any type of flash, looks like that. You have a first step, so the configuration of the flash controller typically. So once this is set, you trigger the operation. The controller sends command and address cycles on the bus. The memory controller interprets those requests and kicks off the charge pumps and the sensing logic to extract the data out of the NAND cells. This takes, of course, a bit of time. There is a wait period until the data is ready in the SRAM. There is an I/O part where we retrieve the data from the flash chip on the host. It may go through an ECC engine if you are using NAND in order to correct the data as well. Problem is there are many sources of latencies or slowliness. So The configuration, of course, is not immediate. The cycles on the bus are slow, basically, even if there are just a few cycles there. The flash array sensing logic might have been kicked up a little bit earlier in some cases. The wait period means the accesses are very serialized, which also has an impact. The I/O retrieval is endless compared to everything else, at least on NANDs. And the correction of the data, of course, adds an extra level of latency. So let's first look at the host side optimizations that are now available. First, direct mappings, of course. Modern SPI controllers have this capability to map some parts of the chip in the CPU address space. So now the forging the SPI packets is left to the hardware, which overall improves the performance. I don't have benchmarks on this one. And more importantly, releases the CPU to do other tasks. So you just make a read on the region, and then you can do something else. So all operations in the SPI memory subsystem go through what we call dir maps. This is the name of the API we've used to capture this feature. When a controller doesn't support dir maps, there is, of course, a fallback over more standard operations where the CPU is in charge. So this has been merged in 5.0. Regarding the other side of my read operation, so when I get the data back on the host, there is the correction that happens on NAND. So this is a NAND-oriented slide. On parallel NANDs, it was by default the host that was also featuring a correction capability. So it was already offloaded to hardware. In some cases, it was relevant to offload to software, especially if you are changing in your design the NAND chip, which now requires a higher level of correction, even though your controller is a bit old and cannot support that. Or in some extreme environments, such as high temperatures situations, you might want to increase a lot the strength, and you will probably need software correction for that. Otherwise, software correction is super slow. On SPI NANDs, historically, which means when the SPI NAND subsystem, which has been created ex nihilo around 4.19, has been introduced, the NANDs were supposed to contain an Hyundai ECC engine, so the correction was left to the chip. But it was a bit slow, barely configurable, and it overall makes the chip a little bit more expensive. So vendors have started removing their Hyundai ECC engine, leaving the duty of the correction to the host controller again. So SPI controllers historically do not feature any kind of correction capability, but now they do. So some controllers have either a pipelined ECC engine, which means really the data flows to the DDR without any copy, or external ECC engines, which are now typically shared with the parallel NAND controller as well, and is also a way to offload the correction to the hardware. The API is super simple. Init and cleanup to initialize the correction, so based on the NAND geometry and its requirements, and then prepare and finish I/O requests before and after every transaction with the chip. So typically, if we take the example of a write, during the prepare operation, the ECC engine would be responsible of calculating the ECC engines and putting them somewhere in the buffer at the end usually. And that's all. Then you let the NAND core do the operation. In the finish side, you have nothing to do. In the read side, it would be the opposite. The prepare I/O request implementation would be empty, and the finish I/O request would have to pick up the ECC bytes, do the correction, and then write the data to RAM and report the bit flips. On the other side of the spectrum, we have the bus. We have the flash chip. So talking again about spinors, spinors are rather slow, especially in the right side. Which means if you start a write operation and then trigger a read, the read will be delayed a lot. And this, when the spinor contains your root file system, may be a problem. So The feature that was brought up by vendors was the read while write feature, which allows, based on the fact that you have an additional cache in the NOR, it allows to do read operations and, well, read the flash array and put the data in a second cache, while the first cache is being written somewhere else in the flash. This requires that you access two different areas of the chip, especially those areas are typically named dies. There is an additional feature in flash speed to measure that. So that just a mention of that tool again, which has been extended to benchmark this kind of improvement. Back on NANDs, we have a problem, which is when we read data, the operations are repeated one after the other. And if you are reading a contiguous region in the NAND array, it's kind of suboptimal. If we look at the timeline at the top, you would start with a read command. You would send the address of the first page you want to read. There is this wait time during which the flash does its magic and retrieves the data in its cache. And then you read the data from the cache. When this is done, you have to start over again, sending a command, a read command, and then sending the address of the page right after, and so on and so forth. This can be optimized. If we tell the chip that we want to read in a continuous manner, it's also called sequential cached reads in some datasheets. While you are doing the IOs on the bus, retrieving the data that is in a first cache, the chip itself may have the capability to read another area and put that into a second cache, so that when the IO from the first cache is over, it automatically switches to the next cache. So it's like reading continuously without those command and address cycles, nor those waiting states. The waiting states are the most impacting here. So in the Raynal subsystem, it's been available since 6.3, but well, honestly, there's been the need for a stabilization period until 6.8. Sorry about that. The benchmark is here. It's improving the speed, but maybe not as much as I originally intended. However, on Spinance, here is a graph that clearly shows another benchmark when we read more and more contiguous pages. You can see that starting from 2 pages right there, we already have a 15% increase on the overall throughput. 25% if we read 3 contiguous pages, and then it levels down at about 40% throughput increase if you read more contiguous pages. This ends at the block boundary. There are 2 reasons for that. Some devices are capable of contiguous reads over the entire chip, but some of them are limited to the die or even to the block sometimes. And because we nowadays use NANDs with GBI more and more, the concept of physically contiguous erased blocks no longer really makes sense. So it's probably not a huge performance hit to just stop the contiguous operation at the end of the block and start it over again at the beginning of the next block when that happens. Now, the last part, where probably the biggest gains have been the bus. So on parallel NANDs, there has been the concept of data interface for a long time, typically SDR timings ranging from 0 to 5, 5 being the highest speeds that we could achieve. So based on the controller capabilities and non-capabilities, we can judge and take the higher speed that is supported on both sides. This has been improved to support something that was part of the specification, the ONFI specification, which are the NVDDR modes, so non-volatile DDR when we sample the data on both edges of the clock, of course. So this brought significant improvements. You can see a benchmark here. So these timings are now supported. They also range from 0 to 5. And there is a comparison on the same platform, the same NAND chip, of course, between SDR Mode 5 and NVDR Mode 5, and we doubled the read speed, for instance, which is rather important. But this is also happening on a NAND that has a huge page size. 16K is rather big, which means the wait cycle is less impacting overall, given the amount of data we read every time we read a page. So it kind of increases the benchmark wow effect. On SPI memories now. Well, SPI memories, well, the SPI bus is slow. We have several pins, a data in and the data out pins, which are the two data pins. Data in is typically sampled on the rising edge of the clock. Data out is sampled on the falling edge of the clock, which is kind of suboptimal. Why just not using the two pins at the same time? And that's dual SPI. So in dual SPI, we sample the data in and data out pins, which just requires switching from in to out internal circuitry a little bit faster. But this has been supported forever in SPI-NOR, and the SPI-NAND subsystem has got support for it since its creation. But what are those two other pins, hold and WP? Are they really useful? Well, if you consider a SPI memory that might be alone on its chip, maybe on the bus, SPI bus, maybe you can just get rid of the hold pin. And the write protect pin, WP, of course matters, but we also have a software alternative for that. So why just not use those two other pins for data as well? And that's the quad mode. So we need to enable quad mode by setting a volatile bit in the SPI memory. And then those four pins are sampled on both edges of the clock. So here is the benchmark. Honestly, I was a bit disappointed again by the improvements. So it may be due to the chip, the time it takes to finish the NAND read. It may also be due to the fact that it's not fully upstream or not upstream at all. The SPI controller might be a bit slow, I don't know. I haven't investigated much. But, well, it still improved the overall throughput. But then, if we have quad support, what about octal support? It's no longer a SPI chip anymore, I guess, but it's still connected to a SPI controller. We have octal chips with 8 data lines. So this has been introduced in 5.1 in SPI-NOR, and way more recently, it will be part of 6.17 for SPI-NAND. Here is another benchmark. So on the TI platform with the Winbond chip, you can see this time the results are massively better, ×5 in terms of throughput. 118 and 188, those are the number of data lines used for the command address and data cycles. 118 means we used 1 data line for the address, whereas we used 8 on the third column. The difference is so small that it's not even measurable with this benchmark. All right, but we are still using half of the capacity until we use double sampling rate, DDR, or in this case, DTR, double transfer rate, probably because data rate meant that the data cycles would be the data would be sampled on both edges. And here transfer means that both the command address, dummy, and data cycles may also benefit from that. So we have yet another set of variants that are possible. It's something that has been supported in SPI-NOR since 5.11 and more recently on SPI-NAND again in 6.14. The comparison with the former platform is a bit better now. You can see we go from 1 megabyte per second to 1.8 megabyte per second with the same chip, just enabling quad mode and DTR mode. But what about octal DDR support, and more importantly, stateful modes? So stateful modes imply that even the command cycles are sent in a manner that we use the same number of data lines and also SDR or DDR in all the cycles. And you remain using this configuration. So here is a Spinor benchmark when we improved the data, the parallelism on the SPI controller. The result here is with the Spinor, so the gain is not as high as we might expect due to the fact that there are big weight states on Spinors. The Spinon core is not yet ready for stateful modes. It's a very interesting feature, but there is a bit work to do as well. It's been expected that every command would be sent on only a single line so far. It's clearly something that I want to work on. All right, but now that we are using octal DDR, an octal DDR bus, can we improve the speed to go even faster? Yes, but not blindly. When you send a read command, again, there is this wait state, which is not supposed to vary with the frequency of the bus too much. It is picturing the wait state on the flash side, and we do not want this to be reduced too much. If we just take the same operation and double the speed, we might we might read stale data or corrupted data because the flash has not been read correctly yet. So the solution for that in the SPI memory world will be to add additional dummy cycles, which means we need to support several flavors of the same command. And that's now possible with this feature, flexible dummy cycles. So every vendor, either Spinor or Spinon vendor, may provide several read operations, identical read operations, with different maximum speeds and hence different dummy cycles, a different number of dummy cycles. So, and this may be a problem if you don't make a wise choice, because if you take the command that might be the fastest and run that at a slower speed, you will spend way too much time waiting, sending dummy cycles. So that doesn't make sense. There is for that an additional layer of complexity to correctly pick the right variant that will be the fastest on your platform. So once again, this is something very new and will be part of 6.17. Can we go even further? Because so far we've been limited to 20 to 60 megahertz buses, maybe up to 100, but not much more. Higher frequency will typically require extra tuning. It's not like you can just turn the speed up and expect good results, because the sampling will not happen correctly. So, small explanation, rapid explanation, hopefully, about the sampling part. When a SPI controller sends the data out to the flash chip, it bases this on its own internal reference clock. So, of course, this cannot work because of the device setup and hold times. You have to delay a little bit the clock so that it's more or less in the middle of the data eye and in a way that the device may sample the data at the correct moment. So we need a transmit delay. We can use default transmission delay at low speeds, but at higher speeds, there will be the need to further tune this value. On the read side, and by the way, even if you do a write operation, there will be basically read and writes on every operation mostly. So they really matter all the time. When you read the data from the chip, the data is no longer synchronized with the reference clock of the controller, because there is an output delay in the flash itself. And when we use higher frequencies, we will also ask the flash chip to toggle a pin that is named DQS. It's a data strobe. So at the same time it latches the data, it is supposed to toggle the DQS pin, so that on the memory, on the host controller side, they are supposed to happen at the same time. And once again, we would tune an RX delay in order to further delay the clock in order to sample the data at the correct moment. Both the transmit and receive delays have a minimum and a maximum value depending on this data I was mentioning before. There is one last delay. The reference clock that the controller uses to extract the data from the FIFO is also no longer synchronized at all with the received data, because there are both delays on both sides, the way in and out. The output delay I was mentioning, the transmit and receive delay as well. So that's a lot of delays, and we might need to further move the window when we look, when the controller reads the FIFO. Otherwise, we might again get the wrong bit. So overall, if we picture that on a graph, we get this square here with a minimum and maximum transmit and reception delay. This is what we can tune on the controller side, minus a diagonal which represents the switch from one reference clock edge to another. And if we want to use really fast speeds, and typically windbound chips have a maximum speed of 166 megahertz, we need to tune those delays dynamically based on the platform. There has been an RFC sent by TI about that, which typically fixes one of those delays, measures the other one, and progressively tries to find the biggest area in this square, and then takes a sweet spot which represents where the data will have the more chance to be correctly sampled. And thanks to that, we have excellent, way better throughputs, because we can really turn up the speed of the SPI bus. You can see here, those were the values I shown. So the same chip was getting us a 2.3 megabytes per second throughput, and on the same platform, just enabling those two features, octal and calibration, we are now at 34 megabytes per second, which is a massive improvement. So what about next? Well, all those almost individual building blocks, I hope they will get together at some point. Everything might be supported. So I'm looking for more NAND chips with all those features supported, and I hope this is going to be called 2026. Thank you very much. And if there are any questions, Yep. I don't know if there is a mic. Yeah, please.
Can you comment a little bit on the OTP support in SPI North? Because there is something, but it's a little bit hidden.
Well, you've seen the OTP support initially. It's something very generic in MTD, and both SPINOR and SPINANS are supposed to have support for that. In SPINOR, there is no support for the factory OTP. I don't know exactly why, if there is no factory OTP or what, but you are supposed to, if there is an OTP, be able to use it. I've seen your patches, your exchanges with the SPINOR maintainers, but yes, indeed, if you really want to use that feature, you need to lock your chip, because otherwise you wouldn't be testing the whole API. You can still read and write with it. To it, there is a user space tool, I believe, part of the MTD utils test suite that should allow you to access that OTP area. Yeah. There is the mic here.
Is support for MLC given up? I mean, are we ever going to get that, you think?
It is mainline. I mean, are you talking about proper MLC support with all yes. the capacity?
Yes, proper.
I can surely tell you that nobody is working on that at the moment. There is a talk from Richard Weinberger and Boris Brezilian, which has been taught many years ago, and I don't think anything that they've mentioned has changed. Nobody has been working on that because it's super complex and we need more data from the vendors, which is not public. And overall, I think there were way too many issues supporting those MLC chips otherwise than by using the SLC pseudomode. So, no. All right. Thank you very much. Oh, no, Marek, sorry.
I'll follow up on that. The MLC chips, can they be switched into this PSLC mode somehow? And do all of the MLC chips support this, or how does this work?
Well, theoretically, yes. At least as far as we know, they should all follow the pattern I've explained very rapidly. But we need to know the pairing scheme in order to support them in Linux. And this pairing scheme is not public, not always. But the problem is, as long as we have, let's say, simple pairing schemes, which are like a space between the two pages both bits belong to, it's okay, because we have support for that. If the pairing scheme starts to be a little bit more funky, we'll, of course, need extra software to support that.
My question was a little bit more, is there some command which you send to the NAND flash which switches it into the pseudo SLC mode, or do you just use half of the capacity?
We just use half of the capacity. Yeah.
Thanks.
At least, I believe. All right. Coffee break, I guess. Thank you.